Hi everyone, and welcome to Intro to Coding, a Carnegie Mellon University Leonard Gelfand Center remote learning class. My name is Shannon, and I'll be your instructor for this course. I'm a third-year student at Carnegie Mellon studying decision sciences and an employee at the Leonard Gelfand Center. This class is broken into 8 activities that explore different aspects of coding. I recommend doing the activities in this order, but you can break them up across a couple days if you'd like, and I've included video timestamps so that you can easily pick back up where you left off. Here's the fun part. Each activity includes an interactive challenge that will provide you with a secret word, and at the end of the class, you'll put together all of these secret words to solve a final puzzle. We'll also be learning some coding vocabulary words throughout the class, which you'll have to remember for our final vocab quiz activity, so make sure you're paying attention. Let's start by talking about computers and coding in general. What do you think of when you hear the word computer? Most people think of a laptop or a smartphone, but in reality, computers are all around us. They could be inside a clock, a car, a home appliance, a piano, a toy, a camera, really anything. The definition of a computer is any device that can store and process data using logical operations. In easier terms, computers are input plus processing plus output. The input is the data that the computer receives from an outside source. The processing is what it does with that data. And the output is the new data it gives back to that outside source. We can think of these steps with the example of baking some cookies. The inputs are the raw ingredients we get from the kitchen, like flour, sugar, and butter. The processing is when we mix all the ingredients together and then put them in the oven. And the output is our finished cookies. Any computer device follows these steps. For example, a calculator could take the input of 1 plus 1 that we type into it. It processes that input by adding the numbers together, and then outputs the answer, 2. But really complex computers follow these same steps. A fancy spaceship is constantly gathering input data from thousands of sensors, combining that data into information like spaceship acceleration and orientation, and using that information to steer or land the ship correctly. Sometimes it feels as if some computers, like robots, have their own brains and know what to do on their own, but that's not what's actually happening. Really, the processing that happens between their inputs and outputs had to be written by a human. We call this coding or programming, when humans create specific instructions for how a computer should function and communicate those instructions to the computer in a format that it understands. These specific instructions for how the computer should function are called an algorithm, which writes them out in steps that the computer can follow. Think back to our example of baking cookies. The recipe is the algorithm that tells us how to do the processing steps of mixing together the ingredients and baking the cookies in the oven. If I didn't have these instructions and just mixed together random amounts of all the ingredients, then guessed how long I should put them in the oven, I bet my cookies would not be very good at all. The algorithm makes sure that the computer is taking the right processing steps. Computer programmers, the people who code the computers, usually write code that looks kind of like this. While this seems difficult to read, it's really doing the exact same thing as a recipe by telling the computer what steps to take to process the input data. Now that you know the basics of computers and coding, go on ahead to Activity 1. First, let's talk about how messages holding the same information can be communicated in different ways. One example that a lot of people experience is different languages. For example, I could say hello to you in English, but I could also say it in a different language and it would mean the same exact thing. Do you know how to say hello in any other languages? That's right, you could say hola, ni hao, ciao, bonjour, and they all mean hello. But you only know how to understand the ones in a language that you know how to speak. How about this example? Look at the message on the screen. Can you read it? Neither can I, and that's because it's not in a language that we can read. This message has been encoded, or put into a special code that hides the original meaning. To retrieve that information, we need instructions on how to decode the message, or undo the code and see the original meaning. In this case, our message has been encoded through a Caesar cipher, where each letter of the alphabet is shifted to another letter. Here, let me show you how it works. We are going to create a Caesar cipher decoder tool. In your worksheet packet on the Activity 1 page are 2 wheels with the alphabet along the edge. Cut out the 2 wheels and put the smaller one on top of the larger one. With a brass fastener, pin the center of the 2 wheels together so that they can spin like this. If you need time to cut out and assemble your cipher tool, pause the video now. You can follow along with this example on your worksheet page where you cut out your cipher tool. This tool helps us both encode and decode a message by shifting the alphabet. You can see my rings are lined up right now so that my A's match, my B's match, and so on, but what if I shifted over one letter? Now I have an A and B together, and a B and C together. To encode a message, we will find each letter from our original message on the outer circle, then replace it with the letter that is right below it on the inner circle. Here's the message I want to encode. Hello. I'm first going to spin my tool around and stop it in some place. It's important that we write down where we stopped it in what we call the key. The key is a little note where we can remember how we shifted the letters so that we can undo it when we decode the message. The key always looks like this: A, an arrow, and then another letter. Find the A on your outer ring and write down what letter is below it. I'm going to put the I below the A, so spin your tool until it looks like this. Once we write the I down, we can start to encode our message. Starting with H, find it on the outer ring, look what's below it, and it now becomes a P. Doing the same thing, our E becomes an M, our L becomes a T, L becomes a T again, and O becomes a W. So this is our new word, PMTTW. It's been encoded. To decode it, we take similar steps. First, you always look at the key to see where to rotate your inner wheel. I want to decode the message that we just encoded, so my key is the same, A to I. So we double check that the outside A is still lined up with the inside I. Now we can decode the message by going from the inside to the outside instead of the outside to the inside. On your wheel, there's a little reminder to go toward the center when you're encoding and toward the outside when you're decoding. So to decode, you find each letter on the inside ring and replace it with the letter on the outside. So we can find P on the inside ring and see that it becomes an H. Our M becomes an E. Our T becomes an L. T becomes an L again. And W becomes an O. We're back to hello. Nice job. That means that we must have decoded it correctly. Now that you know how to use a Caesar cipher decoder, you can find your first secret word by decoding the following message, which is also on your worksheet. The key is A to R, and your secret word is the last word of the message. If you need more help, you can rewind this video just a few minutes to when I was decoding our hello message. Happy decoding! In Activity 1, we learned that the same information can be communicated in different ways, like through different languages or with a cipher. Well, the way that computers understand information is in binary code. Binary code is created from a binary alphabet, which is an alphabet that only has 2 possible values. You can think of them like on and off, yes and no, or true and false, but we communicate them to a computer using zeros and ones. Imagine how much harder it would be to talk to your friends if our English alphabet only had 2 letters, like if every word was only made up of the letters A and B. Having a conversation would sound really crazy. But any message that we could communicate with our bigger alphabet can also be communicated with a binary alphabet. It just looks really different. We can translate our letters into the binary alphabet of ones and zeros using an ASCII chart like this. You can also see this chart on your Activity 2 worksheet. Each digit in binary is called a bit, which is a combination of the words binary digit. 8 bits together is 1 byte, which is the size we need to translate one single character of text like a letter. That's why you can see on this chart that every letter's binary translation is 8 digits long. Using our Activity 2 worksheet, let's translate our names into binary code. I'll go first while you watch, then you can pause the video and translate your own name on your worksheet. First, I put my name into these spaces. Then I go letter by letter and find the byte from the ASCII chart. So my first letter is capital S, which I find here, 01010011. You can see that there's a different code for uppercase and lowercase letters, like the 2 S's here. So make sure that you're using the right one. Next, we have a lowercase h, which is here, 01101000. Lowercase a is here, 01100001. There are 3 lowercase n's in my name, so I can write them all at the same time. They're here on the chart, 01101110, and then a lowercase o, 01101111. I'm now copying this binary into one line, putting a space between each letter. And voila, that's my name in binary. Time for you to pause the video and convert your name now. Your challenge for this activity is to use the ASCII table and now convert binary code back into letters, decoding the following message which is on your worksheet page. Here, I'll do the first 2 letters with you. First, we have 01011001. Scanning the chart, that's here, a capital Y. Next, we have 01101111, which I find right here. It's a lowercase o. Continue decoding the message, and when you finish it, the last word is your secret word. Have fun! Remember that the definition of an algorithm is specific instructions for how to function that are written out in steps that a computer can understand. It might seem easy to write these kind of instructions, but it can be harder than you think. In this activity, we're going to see how well I can communicate simple instructions to you. I've got a drawing here in front of me that you can't see, and I'm going to tell you how to draw it, which you should follow along and do on your Activity 3 worksheet. Then, we'll see how similar our drawings were. As soon as you have your Activity 3 worksheet ready to go, here are your instructions. Step 1. Draw a horizontal line. Step 2. Draw 2 parallel vertical lines. Step 3. Draw a circle between the parallel lines. Step 4. On top of the parallel lines, draw another circle. Step 5. Inside the top circle, draw some smaller circles. Step 6. Halfway up the left parallel line, draw 2 parallel horizontal lines going up to the left. Step 7. Draw 2 new parallel vertical lines under your bottom horizontal line. And step 8. Draw a solid box connecting the bottom of those 2 new vertical lines. Alrighty, pause the video here if you're still working through those instructions. Now that you're done, let's compare our drawings. 3, 2, 1. Here's my drawing. You can see it's supposed to be a tree with a swing set on it. Is this what your drawing looks like? If it is, good job, but my guess is that it looks a little different. If your drawing doesn't look exactly like this, then clearly my instructions weren't specific enough. Let's think of some ways that they could have been improved so that your drawing looks closer to mine. Here's one idea. In step 1, I should have told you to make a horizontal line near the bottom of the drawing that runs the full way between the two sides. Pause the video now and think of 3 more ways that my instructions could have been more specific. Write those 3 ways on the bottom of your worksheet page. Great job participating in this activity. I think you've earned yourself a secret word. Your Activity 3 secret word is swing set. In Activity 3, we learned the importance of writing really specific algorithms when we code. Well, sometimes we don't know if the instructions in our algorithms were specific enough or not until we test them out. Then we can see what works and what doesn't and improve our algorithm step by step until it does what we want it to do. We call this debugging, the process of finding and fixing issues or bugs within computer code. Fun fact, the term debugging was coined by computer scientist Grace Hopper after finding an actual moth inside of her computer. Let's see some debugging in action. I've written an algorithm for making a peanut butter and jelly sandwich. My dad is going to pretend to be my computer, and he's going to follow my instructions super specifically. Then I'll debug the instructions while he tries to do them. Here are my initial instructions for how to make a PB&J sandwich. Let's see how he does. Alright, Mr. Computer, here are your instructions. Step 1, put the bread on the plate. Step 2, put the peanut butter on the bread. Step 3, put the jelly on the bread. Oh no, that clearly is not a peanut butter and jelly sandwich. Let's reset and go through each of those steps individually. Step 1. So my computer put the entire loaf of bread on the plate, and I only need 2 pieces. So first, let me tell him to get 2 pieces of bread from the bread bag. Oh, that's not how you should open the bread bag. I need to tell him, open the bread bag by undoing the twist tie. Perfect. Now I can say, retrieve 2 pieces of bread from the open end of the bag. And place those 2 pieces on the plate. No, not like that. Place those 2 pieces flat, side by side on the plate. Alright, let's move on to step 2. So when I told my computer to put peanut butter on the bread, he put the whole jar, which I don't want. So let's tell him to use the knife to gather some peanut butter and put it on 1 piece of bread. Oh, whoops. We didn't tell him to open the peanut butter jar. Let's add in that instruction. Alright, now use the knife to gather some peanut butter and put it on 1 piece of bread. Oh, I guess I never told my computer how to use a knife. Hey computer, hold the knife handle and dip the sharp end into the jar to gather some peanut butter. Okay, now put that peanut butter onto 1 piece of bread. Well, that's in a clump, so spread out the peanut butter on that piece of bread. Whoa, 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 I don't want peanut butter to be on both sides. Here, let me get you a new piece of bread. Alright, this time I want you to spread the peanut butter on one flat side of the piece of bread. Okay, perfect. And for step 3, we should be learning from our last step. So for this jelly step, let me first tell you to open the jelly jar. Hold the knife handle and dip the sharp end into the jar to gather some jelly. Oh no, it looks like you didn't get any jelly that time. Repeat that last step until the knife actually has some jelly on it. Put that jelly onto the other piece of bread. And spread the jelly around on that one side of the piece of bread. Great! Now we just need to make this into a sandwich. Hey computer, put the 2 pieces of bread together. Oh, not like that. Put the flat sides of the 2 pieces of bread together. Ugh, oh no, that's wrong too. Put the flat sides of the 2 pieces of bread that have the peanut butter and jelly together. Perfect. Now drop the sandwich back onto the plate. And there we go, we have a finished peanut butter and jelly sandwich. You can see it was really difficult for me to make my algorithm specific enough that my computer knew exactly how to make the sandwich and wasn't messing up in a bunch of different ways. If you have a partner available who can be your computer, I have a challenge for you. If you look at the Activity 4 worksheet page, there's a space for you to write out an algorithm teaching your computer how to tie your shoes. You can write your initial algorithm, have your computer follow those steps, and then write a couple ways that you need to debug your algorithm by making it more specific until your computer is doing the exact right thing and successfully ties their shoe. Good luck! Oh, and your secret word for this activity is shoelace. Let's see how good we are at following an algorithm that looks more like computer code. This activity will teach us how to understand and follow coded algorithm steps through a fun board game. This is what our algorithm instructions are going to look like. Each step will be on a different line, which you read from top to bottom. So this algorithm here is telling me to go forward twice, then turn right, then go forward 3 more times. I've put a little key in the corner of the screen to help you remember which way is left versus right. Let's prep our game, then we'll start reading some simple code. Pull out the game board from your Activity 5 worksheet pages. For this activity, you'll also need some sort of character to move around the board. You can take a piece from another board game like I did, or use something like a penny or an eraser. But your character does have to be able to face a certain way. So if you have an item like a penny, make sure to add an arrow to the top so you know which way it's facing. In each round of this game, you'll start your character standing on the star and facing forward. Let's begin with example number 1. The code is here on the right, and I'm going to follow it line by line. So I'm going to move forward, move forward, move forward, turn to the left. So now my character is facing in this direction. So I'm going to move forward again in that direction, move forward again. I turn right, so now my character is facing this way. Turn right again, and now they're facing this way. So now I'm going to go forward in that direction once, 2, 3, and 4 times. We're going to turn left and go forward 1, 2, 3 times. So we've ended on the letter C. You might have noticed that there were a lot of repeating steps in that algorithm. Well, instead of writing 4 move forward steps in a row, I can use a loop, which is a command that tells you to repeat certain steps of the algorithm. Loops are nice because they usually take up less space than writing out the repeating steps. Loops look like this. First, you have to announce that you're about to start a loop with this line. Then under that, you put the steps that you want to repeat. Make sure they're indented, pushed a little bit to the right, so that you know which steps to loop and when to stop looping. And finally, you add in the number here of how many times you want to loop those steps. Let's really quickly rewrite that algorithm we just followed, but with loops. So I'll make any repeating steps into a loop. We have a couple places where I move forward a couple times in a row, so I can make those into loops. And right here, I turn to the right twice, which I can also make into a loop. Now you can see that this algorithm is much shorter, it takes up less steps, but let's run through it again. So I'm going to move forward 3 times, turn left, move forward twice, turn right twice, move forward 4 times, turn left, and move forward 3 times. And look, I still end up at the same place on top of the letter C, which means that we wrote our loops correctly. Let's follow another algorithm with loops. So we're going to start off with a loop that we should move forward 6 times. Then I turn left. Now in this next loop, we have multiple steps. So we have to go through each step that's inside of the loop and then start back up at the top. So for this one, we're going to move forward and then turn right, and then move forward and turn right. Make sure you loop everything that's indented together instead of doing them separately. So this loop is telling us to do forward, right, not forward, forward, right, right. Sometimes loops can also be inside of other loops. We call this nested loops. So I first look at the outside loop and I see that I need to do everything inside of it 3 times. Well, the first thing inside of it is another loop that I need to do 4 times. So let me move forward 4 times and then turn left. So I've gone through the outer loop once and need to do it 2 more times. So let me go back to the inside, move forward 4 times and then turn left. And one last time, move forward 4 times and then turn left. So this algorithm ends on the letter H. Okay, let's do one last example. This example is going to include conditional statements. Conditional statements give you algorithm steps to follow, but only if a certain condition is met. They're also called if statements because the first thing you see is this piece of code, where you check whether or not the statement that's here is true. If it is true, then you do the steps inside of the if statement that look just like the steps inside of a loop. But if the first statement is false, then you completely ignore the steps that are inside of the if statement. So let's do this example. First, we move forward 4 times, and we have a conditional. So if we are standing on letter C, then we are going to turn right. Well, I look, and we are standing on letter C, so let's turn right. Now I have a loop telling me to go forward 3 times. All right, and now if I'm on the letter G, then I'm going to move forward. Oh, but look, I'm not on the letter G, so I can completely ignore that instruction. I'm now going to turn left. If I'm on letter F, well, I am, so let's follow those instructions. So first, I move forward twice, and then I turn left. Okay, if I'm on the letter D, which I am, so I'm going to read those instructions, and I have a loop inside of an if statement. So I need to go forward, forward, turn right, and then loop it again. Forward, forward, and turn right. All right, and one more if statement, if I'm on the letter A, oh, well, I'm not on the letter A. So I can completely ignore those steps that are inside the if statement. I don't even need to know what they say. So that's the end of our algorithm, and we've ended on the letter Z. Those examples were kind of hard. If you need more practice, especially with loops or if statements, you can go ahead and rewatch them. Whenever you're ready, pull out your other Activity 5 worksheet page, which has 4 challenges for you to do. Just like I did in those activities, I want you to follow these instructions, starting your character on the star each time. Once you get through the algorithm, write down the letter that your character ended up on. The 4 letters that you get are going to spell out your secret word for Activity 5. Feel free to ask an adult for help if you need some extra tips. Now it's your turn to write some algorithms. In this activity, you're going to be taking on the role of a honeybee who has to communicate to the other bees the route necessary to find some nectar. Pull out both of your Activity 6 worksheet pages and first cut out the cards on the second page. These are both your game pieces and your algorithm instructions that you'll be building. This game has 4 steps. First, we place the hive and the flowers on 2 random squares of our game board. So let me place them here and here. Then we envision a route our bee could take to get from the hive to the flowers. So think of this route in your mind and imagine it as a red guideline across your game board. So I'm going to try to follow this route. Next, we need to write an algorithm that will tell our bee how to follow this route. So you'll use the algorithm game pieces that you just cut out. Remember that when we write an algorithm, we put 1 piece of instruction on each line, and our instructions go from top to bottom. So to follow this route, what I think I need my bee to do is go forward 3 times, then turn right, and go forward 2 more times. So I'll take my algorithm pieces and write out those instructions. First, I have 3 move forward blocks, then a turn right block, then 2 more move forward blocks. And finally, we test our algorithm out using our bee. So let's start our bee on the hive and now follow each of the steps that we've written. So my bee moves forward, moves forward, moves forward, turns right, moves forward, and moves forward. And great, we've ended up on the flower. For the next example, I'm going to put my hive here and my flower here. It should be really easy for our bee to go in between the hive and flower. If it's starting at the hive, it just needs to turn right and then move forward 4 times. But what if I add in some walls? If you take these orange lines that you cut out on the second activity page, we can add them to the grid as walls that the bee cannot move through. So now, our bee is going to have to take a longer path to get to the flowers. First, let's envision what that path is going to look like. I think I'll follow this path. Now let's turn it into code. So if our bee starts facing forward, first it needs to turn left, then it will need to go forward, turn right, go forward 2 more times, turn right, go forward 5 times, turn right, and go forward twice. Let's test it out. So we'll start with our bee on the hive, turn left, go forward, turn right, go forward twice, turn right, go forward 5 times, turn right, and go forward twice. Yep, we made it to the flower. Remember that in Activity 5, we learned that a loop is a command that tells you to repeat certain steps of your algorithm. If we look at the algorithm I made for the last example, there are a couple repeating sections that I can turn into loops. For example, right here, I turn right and go forward twice, then turn right and go forward twice more, which I can turn into a repeating loop. I can also turn these other 3 forward steps into a loop. Let's follow the code again to make sure it still leads us to the flowers. So I'm going to turn left, move forward. The following loop I need to do twice. So I turn right, go forward, and do it again. Turn right, go forward. I go forward 3 more times. I turn right, and I go forward 2 more times. Yep, we still ended up on the flower, so our code is written correctly. Now it's your turn. Reset your flower and hive to new locations on your game board, and write out your code for your bee to get from the hive to the flowers. If you have a partner like a parent, you can write out your algorithm and see if they can follow it correctly to get to the flower. Otherwise, you can write out the instructions and test them yourself. Do this 3 different times with new flower and hive locations, using loops and walls at least once if you can. Pause the video now and come back when you're done. Awesome job! Now you have some practice writing out an algorithm of your own. Your secret word for this activity is buzz. See you in Activity 7! In this activity, we're going to keep writing some real code. We'll be coding in the Python language, so after this activity, you'll have some basic Python knowledge. Let's use Python to create some functions. A function is a section of an algorithm that follows its own computer-like steps of taking inputs, processing those inputs somehow, and outputting a new value. So one algorithm could contain just one function, or it could contain multiple functions that you read and complete from top to bottom. In Python, functions look like this. The first line has the function name, and then parentheses where you write the inputs. In functions, these input values are also called parameters. Then, indented from the first line, you write whatever calculations you want to do with those parameters. Finally, the last line says the word return, followed by some value, and that value is your output, or essentially the answer to that function. The functions we learn how to do today are going to look like this. You might be wondering why there are shapes in this function. Well, these shapes are representing variables. Variables are like programming storage bins that can hold a value so that it can be used in multiple calculations. I think the easiest way to show you this is through an example. So on the left here, we have a function, and on the right, I have my workspace. Notice that this setup looks exactly like your Activity 7 worksheet pages, so you can follow my same steps when you practice with those worksheet problems in a little bit. This top line here is telling me the problem I need to solve. So it's telling me that I should solve this function using the number 2 in place of the circle parameter. Well, because I know that the circle equals 2, the first thing I should do is write that here in my variable space. This is where I'll write all of my variables' current values so that I can remember them. Once I've transferred that parameter, I can check off my first line. Next, this is telling me that the star equals 11. So let me fill that in the variable space as well. Now we get a little more difficult. So the triangle equals the star minus the circle. Well, if I look over here, I see that the star equals 11 and the circle equals 2. So down here in my scratch work section, I can rewrite that the triangle equals 11 minus 2, so the triangle equals 9. And I'll add that up here in my variable space. Next, we have that the star equals 4. But look at that, we already wrote that the star equals 11. Well, remember how I said that these shape variables are storage bins that just hold a certain value? If a variable gets set to a new number, it simply replaces the old number in that bin. So I can just cross out 11 and write that the star equals 4 now. Next, we have that rectangle equals triangle plus star. Again, over here, I'll write that rectangle equals, well, the triangle is 9 plus the star is 4. So the rectangle equals 9 plus 4, or 13. And finally, I'm going to return or output the rectangle's value. Well, we just calculated that the rectangle equals 13, so 13 is my final answer. That wasn't too hard. Let's do a couple more examples to get more comfortable. All right, here's our next example. So once again, we're going to be solving this line by substituting 4 for the star parameter. So we'll go through the function line by line, using our right side here to fill in variables and do our scratch work. So first, because I'm plugging in 4 in place of the star, I can write that star equals 4. Next, my rectangle equals star plus 3. That means that rectangle equals 4 plus 3, rectangle equals 7. So let me fill that into the variable space. Next, we have an if statement within this function. Remember that with if statements or conditional statements, you only complete the indented steps if the top line is true. So here, we check whether rectangle equals 7. Looking at my variable space, it does, so we should do the line under it. So star equals star plus 2. How can something equal itself plus 2? Well, this is just another way that we can update a variable. Star currently equals 4, so I'll write down in my scratch work that my new star is going to equal the old star, or 4, plus 2. So star now equals 6. And in the variable space, I'll replace my 4 with a 6. Next, we have another if statement, so if star equals 4, but looking at the variable space, it no longer equals 4, it now equals 6. So because that statement is false, I do not do the line indented underneath it. And next, we have that circle equals rectangle plus 3. So again, I'll make my notes. Circle equals, well, rectangle is 7, so circle equals 7 plus 3, so circle equals 10. And finally, we return circle, so I check circle's value, which is 10, and I put that as my final answer. And let's do one last example. This example is different because we have multiple parameters. You can see that our function takes the input of both a star variable and a rectangle variable. When we have multiple parameters, we separate them with a comma, like you can see here. Because our function has 2 parameters, the statement that we need to solve also has 2 parameters. So this is telling us to put a 6 in place of star and a 4 in place of the rectangle. So let me fill both of those in my variable space. All right, then we have that triangle equals star plus 2. So triangle equals 6 plus 2, so triangle equals 8. Next, circle equals triangle plus rectangle. So circle equals triangle is 8 plus rectangle is 4, so circle equals 8 plus 4, so circle is 12. Next, we have an if statement. So if circle equals 10, well, circle doesn't equal 10, so I can ignore the indented statement. And finally, heart equals rectangle plus star. So heart equals rectangle is 4 plus star is 6, so heart is 4 plus 6, or 10. And finally, I return heart, so my final answer is 10. Great job! Those were some difficult functions, so feel free to rewatch if you need some more help. When you're ready, take out your Activity 7 worksheet pages, where there are 4 more examples for you to solve. Once you finish all 4 examples, Go to the third Activity 7 worksheet page, where your answers to those 4 questions will reveal your secret word. So for example, if my answers to the 4 questions were 2, 17, 9, and 11, then my secret word is stamina. All right, for our final activity, I'm going to be testing your memory of all the new concepts we've learned throughout the class. Pull out your Activity 8 Vocabulary Review worksheet page. You can see 9 definitions of vocabulary words that we learned throughout the introduction in the last 7 activities. On the right, there's a word bank of all the vocabulary that we've learned. For each of the definitions, find the corresponding vocab word from the word bank, and in the space to the left, write the letter in front of that word. So if I thought number 1 was the definition for binary code, I would write the letter E right here. Once you identify all of the definitions, these letters from top to bottom will spell out your final secret word. Pause the video now to complete this vocab activity before moving on to our final puzzle. It's time for you to solve the final puzzle. Pull out your worksheet pages 16 and 17. On page 16, first transfer all of the secret words that you've gathered from each activity into this one list. Then, that list is going to become your word bank for the word search on page 17. Find each of those words in the word search and draw a line through it. Finally, transfer onto these blanks the remaining letters from the word search that aren't crossed out. So for example, if this was my word search and the 2 words I need to find are yes and echo, I'd find and cross out those 2 words. So here's yes and here's echo. And then I'm going to go across each line and write down the letters that are left. So on the first line, I have B and R, next line A, then I, and then N. So my secret message from this puzzle was brain. Follow these steps on your worksheets and fill in your answer to the following joke. How do you keep a programmer in the shower all day? Pause the video now and complete the puzzle. All right, did you solve the puzzle? Your answer should be, give them a bottle of shampoo that says lather, rinse, repeat. Do you get the joke? Here's a hint. Remember when we were talking about loops in activities 5 and 6? A super important step for writing a loop is telling the computer how many times to do the loop. If we don't, and we simply tell the computer to repeat, it might get stuck in an infinite loop where it keeps repeating the same steps and can never move on in the algorithm. So if a programmer reads a shampoo bottle that says lather, rinse, repeat, they might get stuck in their own infinite loop of washing their hair and never finish their shower. Congratulations on finishing this Introduction to Coding class. I hope you had some fun learning some programming basics with me. Together, we explored what makes a computer and how to communicate with computers, the importance of writing really specific algorithms, and we even read and wrote some code of our own, including some code in the Python language. If you enjoyed this class, you can find others like it on the Leonard Gelfand Center website. If you go to cmu.edu/Gelfand, click on the Gelfand Outreach tab, and then click on Remote Lessons, you can find other classes meant for different age groups. I want to give a quick shout out to Mr. Wernz for helping me film sections of this course, and to Pam at the Gelfand Center for her guidance in planning it. Thanks for watching!